Dear students, today we are going to discuss the last topic of this chapter. See, these topics will not be available in your textbook, so I will be sending images of this topic. Okay. Anyway, even it is not available in your textbook, you have to read this and you have to understand what it is told in this topic. Okay, right? Coming into the topic. Already we studied about resistivity, isn't it? What was the unit of resistivity? It's ohm meter. Okay, right. So the letter or the symbol of resistivity is rho. And we studied the equation R equal to rho L by A. Actually, this resistivity was a constant. When we were studying the factors depending upon the resistance, we got that it is proportional to the length, it is inversely proportional to the cross-sectional area, and from there we got this point, resistivity. See, if you are considering a conductor, a piece of conductor, it should have got a resistivity, isn't it? It have a resistivity. And this resistivity value actually changes according to the temperature. So how it changes? Let's see. So what happens if we conduct the current continuously for 1 hour in a circuit? What happens if you put your mobile in charge for a 2 hour or 3 hour? What happens, or what you feel when you touch the charger? You feel heat, obviously, isn't it? As like that, when the temperature increases after a long period of time, here the resistivity also observe a small change. So the resistivity will also get increased or decreased according to the temperature. So if you have a conductor at room temperature means temperature in the atmosphere. Maybe nowadays it will be 24 degrees Celsius or 25 degrees Celsius. So at room temperature, the resistivity may be, at room temperature, we can give that room temperature as T1 degrees Celsius. At T1 degrees Celsius, the resistivity may be rho 1. And what happens after some time? The temperature increases into T2 degrees Celsius. At this time, the resistivity also may increase or decrease, and it becomes rho 2. Hope you understand. The resistivity will change after some time. So there is a factor called temperature coefficient of resistivity. It's alpha, new symbol for you, alpha. As like infinity, the symbol of infinity or proportional. So alpha is called temperature coefficient of resistivity. See, alpha is defined as the change in resistivity divided by original resistivity into temperature. See, for what we are, what is alpha? What is the definition of alpha? You may be getting confusion. Don't worry. Just understand that if you have a conductor and if you have the resistivity rho 1, after some time, if the temperature changes, there will be a change in the resistivity also. To measure this change in the resistivity, we introduce a new term that is called alpha. So alpha is the temperature coefficient of resistivity. Temperature coefficient of resistivity, and its definition its equation is change in resistivity divided by original resistivity into temperature. That is the difference in temperature. See. So as I told that, let me write this thing here. Change in resistivity divided by original resistivity into temperature. Actually it is the change in temperature. Change in temperature. So alpha is defined as the ratio of original resistivity to the ratio of change in resistivity to the original resistivity and temperature. Now, what was the change in resistivity? The first resistivity was ρ1 and the second one is ρ2. So the final minus initial will give us change in resistivity, that is ρ2 minus ρ1. Now here, what was the original resistivity? Original resistivity is ρ1. That is the first resistivity of the material. And now change in temperature. At first it was room temperature, T1 degrees Celsius. After some time it gets converted into T2 degrees Celsius. So change in temperature is T2 minus T1. Simply, this is the equation for temperature coefficient of resistivity. See, alpha equal to ρ2 minus ρ1 divided by ρ1 into T2 minus T1. So, if a conductor or a circuit is working, obviously temperature will increase only, isn't it? Temperature will not decrease according to the working of a object. So, if temperature is increasing, if resistivity also increases, if resistivity increases means ρ2 will be greater than ρ1, isn't it? Are you getting? We have a conductor and its resistivity is ρ1. After some time, the temperature increases, and that time the resistivity becomes ρ2. Accordingly to the temperature increase, if resistivity also increases, the value of ρ2 minus ρ1 will be a positive value, isn't it? If it was ρ1 was 5 ohm meter, and ρ2 is equal to, after some time the temperature increases and it becomes 10 ohm meter. So what happens? It's a positive value. 10 minus 5 will give us 5. What happens in the opposite case? If resistivity is, the first resistivity is 10 ohm meter, and after some time the temperature increases and the resistivity becomes 5 ohm meter. What happens in this case? The value of alpha will be 5 minus 10. In that case it will be negative. So accordingly to the increasing temperature, if the value of resistance also increase, value of resistivity also increase, alpha is a positive value. So how alpha become positive? According to the increasing temperature, if the value of resistivity also increases, then alpha will be positive. Alpha is negative in the case temperature will increase, but if the resistivity decreases, alpha becomes negative. Why I am describing these alpha and all these terms? This is not at all important for you. These things are not at all important for you. But this thing is important. That's why you will not understand what is alpha. Alpha is positive or alpha is negative when I tell it directly. So that's why I explain all these terms. So for every conductor, according to the change in temperature, the resistivity also feels a small change according to the change in temperature. Resistivity may increase or decrease. In order to find the change in the resistivity, to measure the change in resistivity, we introduce a term called alpha, temperature coefficient of resistivity, and its equation is change in resistivity divided by original resistivity into change in temperature. That is, final resistivity minus initial resistivity gives us change in resistivity. Original resistivity is ρ1 and change in temperature is final temperature minus initial temperature. And see, what is the unit of this alpha? Change in resistivity by original resistivity. The unit of resistivity is ohm meter, isn't it? Here also one resistivity is here, ohm meter. So what happens? They get cancelled each other. So we need not go for the unit of resistivity. Now the rest term is this temperature. So it becomes 1 by C. 1 by C, or we can write it as C inverse. So centigrade inverse is the unit of alpha. See, these points are important. Alpha is positive The temperature coefficient of resistivity is positive when resistivity increases according to the increase in temperature. Alpha is negative when resistivity decreases according to the increase in temperature. So that's the 2 points. Now coming to our main point. So based on this resistivity, the materials are divided into 4. You already know, based on conductivity, materials are divided into conductors and insulators. As like that, based on resistivity, the materials are classified into conductors, semiconductors, insulators, and superconductors. So conductors are those materials, which allow the passage of current completely through it. And we are telling based on resistivity. We are classifying them based on resistivity. So we have to give a definition based on resistivity for conductors. So those materials whose resistivity is in between 10 raised to minus 8 and 10 raised to minus 6 ohm meter is called conductors. Those materials whose conductivity is in between the range 10 raised to minus 8 and 10 raised to minus 6 ohm meter is called conductors. An example: silver. Silver is the most conducting material. Okay. And its resistivity is 1.6 into 10 raised to minus 8 ohm meter. The next one is copper. The conductivity of copper is 1.7 into 10 raised to minus 8 ohm meter. See the range? They are all belonging to the same range, 10 raised to minus 8 ohm meter. So this is the resistivity of silver, and the second one the resistivity of copper. Do I told conductivity? Sorry, it's resistivity. Resistivity of silver and resistivity of copper. So conductors are those materials whose resistivity is in between, whose resistivity is in the range of 10 raised to minus 8 and 10 raised to minus 6 ohm meter. So that is the definition for conductors on the basis of resistivity. And see, their alpha is positive. What is alpha positive? Their resistivity increases when we increase the temperature. So the resistivity increases when we increase the temperature. Remember the point. So these are the 2 points to classify the materials based on resistivity. The 2 points are based on resistivity. Alpha is the temperature coefficient of resistivity, and this is the direct resistivity range, 10 raised to minus 8 to 10 raised to minus 6 ohm meter. Hope it is clear for you. Now moving to the second one. Semiconductors. So these are the materials whose value, resistivity value, so up to 10 raised to minus 6 we already discussed it. So from 10 raised to minus 5 to 10 raised to 2. Those materials which have the value, which possess the value 10 raised to minus 5 to 10 raised to 2 ohm meter. These are called semiconductors. Those who have the resistivity value 10 raised to minus 5 to 10 raised to 2. And remember, their alpha is negative. That means their resistivity decreases when the temperature is increased. And the next one, insulators. Their resistivity range is in between 10 raised to 10 and 10 raised to 17. And it may go up to 10 raised to 18 or okay. So just remember this range, 10 raised to 10 to 10 raised to 17. Let me confirm. Okay, right. 10 raised to 10 to 10 raised to 17 ohm meter. This is the resistivity range of insulators. Their alpha is also negative. That is, their resistivity decreases when we increase the temperature. This point we have to note down. Now, superconductors. Actually, there's a story behind superconductors. So there was a physicist, a Dutch physicist, Camerling Ons. And when he was doing some experiments, I think it is 1896 or something, okay. Sorry, 1911. In 1911, a Dutch physicist, Camerling Ons. So he was doing some experiment with mercury. He found that the resistivity range of mercury, actual resistivity range of mercury is 96 into 10 raised to minus 8 ohm meter. That is, it belongs to the category conductors. And actual resistivity range, this resistivity decreased to 0 when the temperature is changed into 4.2 Kelvin. When the temperature was brought under 4.2 Kelvin, the resistivity from 98 into 10 raised to minus 8 ohm meter is changed into 0. The resistivity becomes 0. So hence he named this as superconductors. That means they are not only conductors, they show very high amount of conductivity. Resistivity is just reverse or the reciprocal of conductivity. If the resistivity of a material increases, that means the conductivity will be decreased. See here in this case, 10 raised to minus 8, such a small value, 0.000. After 8 zeros, 7 zeros, the next digits come. So such a small value it possesses. That's why its conductivity is high. That is why silver 1.6 into 10 raised to minus 8 comes in first in the range, first in the list, because it has such a low resistivity value. So here, from a 96 into 10 raised to minus 8 ohm meter, its resistivity changed into 0. And see, it was done when it was changed into, the temperature was changed into 4.2 Kelvin. And after that, many other scientists who experimenting on these things, some of them experiment based on the oxides of barium and lanthanum, and they found that their resistivity also decreased on certain temperature like 176 K or something. And nowadays scientists are taking effort to find some materials which become superconductors at 300 Kelvin. What is the importance of 300 Kelvin? 273 Kelvin equal to 1 degree Celsius, isn't it? So 300 Kelvin means 273 plus something. What is that something? Here, how many we have to add? We add 27. 7 plus 3, 0. 9 plus 1, 10, 0. Here, 3. So 27. 27 is almost the room temperature. So scientists are finding or searching for a material which becomes superconductor at 300 Kelvin. So that what happens, if a material becomes superconductor in room temperature, it will be such a huge invention in the case of electricity. We can transmit the current from one point to another point with zero loss. Nowadays we are losing a lot of current when we are transmitting it from one end to the other due to the resistance and resistivity of the conductor. But what happens if resistivity is changed into 0? We can conduct more current from one point to another. So nowadays scientists are working for this to find a material which becomes superconductor at the 300 Kelvin. So this temperature below which a material becomes superconductor is called critical temperature. What is called? Critical temperature. Critical temperature. So these are all about conductors, semiconductors, insulators and superconductors. So hope you understood conductors that belong to the range 10 raised to minus 8 to minus 6, 10 raised to minus 5 to 10 raised to 10 raised to 10 to 17, and these are the materials which becomes or whose resistivity becomes 0. That's also based on resistivity. Resistivity becomes 0 under a certain temperature. So that's all about the classification of conductors. Now, human body and its conductivity. Do human body conduct electricity? We'll get shocked, isn't it, when we try to conduct electricity. See, a dry human body have a resistance of 50 kilo ohm. A dry human body will resist to the current by an amount of 50 kilo ohm, which is equal to 50 kilo ohm means 50,000 ohm. And a wet human body have a resistance of 10,000 ohm, 10 kilo ohm. Normally, our electric circuit, which is running on 220 volt. So the potential difference is here, resistance is here. Let's calculate the current flowing through our body when we touch in an electric circuit. I is equal to V by R, isn't it? Here V is equal to 220. 220 divided by, in the case of dry body, 50,000. 50,000. So let's cancel 22 become 11. So it's 11 by 2,500. 11 by 2,500. It's almost 0, 0. Thousand remaining, then 5. So it's 0.0045, or we can write it as it's almost 4.5 into 10 raised to minus 3 ampere. That is equal to 5 milliampere. 10 raised to minus 3 ampere means milliampere. So it's almost to 5 milliampere. And in the case of a wet body, I is equal to V by R. Okay, 220 divided by. In the case of wet body, it is 10,000. Okay, it is 22 by 1,000. Easy to calculate. 22 by 1,000. We have to just put 2 zeros in front of them. That is 22 into 10 raised to minus 3. Directly from here also we can write 22 into 10 raised to minus 3. So it's 22 milliampere. 22 milliampere. It's ampere in ampere. 22 milliampere of current. See, this 22 milliampere of current is enough to give us a shock, because our body is very sensitive to electricity, and that's why it gives us a severe shock. So this is in the case of our household things. What happens when we touch in a 11 kV line? 11 kV. That means here volt is changed into potential difference is equal to 11 kV. V is equal to 11 kV. That is 11,000 volt. 11,000 volt. So that time I is equal to V by R. Even if our if our body is a dry body, let us calculate for that. It will be easy for us to calculate. Then okay, V is equal to 11,000. 11,000 by 10,000. 11 by 10 is equal to 1.1 ampere. See, 1.1 ampere of current will pass through our body at that time, and this enough to make us severe injuries. And you can see this is in the case of a dry body. If it is in the case of a it is in the case of a wet body. If it is in the case of dry body, you have to divide 11,000 by 50,000, which will also give us 0 point something, 0.2 or something. It will give us. See, that's enough to make our nervous system to be demolished. Our heartbeat will stop and eventually lead to death also. So This is very severe. Never touch an electric circuit with bare hands. You have to use gloves, and if possible, do not go to that area and never try to touch in this device. Okay. So these are the mathematical calculations of how much amount of current will be passing through the human body in 1 second. This moment we touch them. Okay. So that's all about human body and the current passing through the human body. The next one is some of the practical applications of these conductors. Is there some practical applications based on these conductors, insulators, and these semiconductors, all these things? Already discussed what is the advantages of superconductors. In order to make a circuit, the scientists are trying to find a 300 Kelvin critical temperature material in order to transmit the current from one point to another point without any loss. Now, there are some materials like tungsten. You know what is that? This is the filament inside the filament bulb. There is a tungsten wire, you can see, and the tungsten have low resistivity and high resistance, and high melting point also. Due to high resistance, when the current flows through them, high resistance means that material will try to stop the current. So when it tries to stop the current, heat is produced. So for everything that is used for making heat, it should have high resistance, and it have high melting point too. Because of that high melting point, this will not break. It will break only after achieving a 33,000 Kelvin or something. It's all about tungsten. 33,000 something is the melting point of that tungsten. So only when it reaches 3,000 something. So only when it reaches 3,000 something range, only it will melt. So due to high resistance and it will not melt, it tries to give us light. The heat and light together produced by a filament. Such like this tungsten, there are other materials too. Some of them are alloys. What is alloys? They are the mixture of two or more components. By mixing two or more components also, we made some specific components used for our electric circuit. Why we mix these 2 or 3 components together? Why we make alloys? That is, so that we can get the advantage of each material. Some of them will have low resistivity, some of them will have high melting point. So in order to get all the advantages from these methods, we are making alloys also. So I will give you this images of this thing. It is not available in your textbook, so you have to create a note on based on this. So that's all about our chapter. Our chapter is completed now. This was the last topic. Hope this chapter is easy for you. Don't be confused in the term temperature coefficient. It's not so important, but the only term that is important is alpha is positive and negative. You have to understand that term. In order to understand, make you understand that term, I discussed about the equation of alpha and something. Then only you will get to understand what is alpha. Okay. Other things are just general things, the human body and the electric shocks related to human body. That's all general things, tungsten and the classification of materials. That's all general things. Okay, and thank you. Have a good day.